is on our current work in progress and our ideas on predicting the runtime cost of database operators. But before we get into the details, I want to start with a short introduction and motivation. So what are the use cases for cost predictions in database systems? And the one that's probably most known is for the query optimizer that uses cost estimations to choose between different query plan options and then pick the cheaper one. But there are, recently there are some other use cases. For example, in cloud environments, the vendors can use cost predictions to estimate the cost of running a customer workload. And by doing that, they can optimize their resource planning and allocate the resources cost efficiently. And last but not least, for self-driving database systems, these systems really need to precisely quantify the impact of the actions they are taking so that they can choose the right configuration to apply to the system. But cost estimation is a database problem that is almost as old as database systems themselves. So I think that building right cost estimation models is becoming increasingly challenging. In the past, models were usually handcrafted and manually built by database architects, but I believe that nowadays the complexity of the environments where we deploy our database systems in is too high to actually represent the complex reality. And this is for a couple of reasons. For example, because we deploy our database systems on different hardware. When we think of the cloud, we might deploy them on different CPU architectures, ARM, IBM, or Intel CPUs. The database operators might even run on the GPU, and we don't know on the layer of the memory hierarchy where we where we store our data can also have a large impact on query execution and operator execution time. Another aspect are database configurations. So depending on how the data is partitioned, if the data is compressed in the database, or if I have indexes that I can use for query execution, this might have an impact on the operator execution time as well. And last but not least, depending on the data that I'm operating on and the workloads I'm running, this can also highly impact the execution time for database operators. So taking all of that into account, what are requirements for cost estimation models nowadays? Of course, what I always want for such estimation models is a high estimation accuracy, and especially for the cloud and the self-driving use case, this is really important. But as I said, because we deploy our systems in so heterogeneous environments, I think that we need context-specific and custom-made models for all of these environments where they run in. And taking this into account, I think that we cannot pre-train the models, but we have to train them online, basically. So when the database system is about to start, we train a custom-made context-specific model, and if we want to do that, we have to take the training time into account, because we cannot afford to delay the system start for too long while we are building our models. So some model architectures or some model types might not be the right choice for this approach if they train for a couple of hours. And last but not least, because the circumstances where my database is running in can completely change. The workload can change, the dataset can change, and even the hardware in the cloud can run, where my database system is running can change. I need a way to adapt to the changed circumstances and reflect that in my model. So the idea to learn cost models based on query execution and operator execution observations is not new. But I want to quickly go over high-level overview how this is done and what are our adaptations to that. So in the first phase, we call it calibration phase, we need to generate observation data that we can later train our models on. And in the literature, often typical database benchmarks like the TPCH is used as a as basis for generating the calibration data. So we're using the TPCH dataset and queries, run them in our database, extract features from the recorded execution and the runtime, and we use this as basis to train our models on. What we actually do differently here is that we don't use the data for training a single model, but we are dividing the problem into several small problems and create many small expert models for the different heterogeneous domains. For example, for the different encodings in our database systems, we create one model for each of these encodings. And when we split the data, we train our models, and in the last phase, the operation phase, we use the cost model to actually estimate the execution time of the database operators. And what we also do is we monitor the performance of the cost models, and when the error is too large, we take the newly gained observation data during operation and feed it back into the model to improve the model while it's operating. So how does our setup look like? It's also, some parts of this are also a small comparison to related work. So most of the literature is implementing cost models in Postgres, which has a different architectural approach to our system. We are implementing the cost estimation in our research database system HiRise, which is a columnar main memory database system with a column at a time execution model. And then there's another difference. Most of the other work is using popular database benchmarks like TPCH as training data. We are generating our own data set, and I'm not training on the data from the database, from the benchmarking workload. And we are trying to generate a calibration data set that the model can use so that it can later generalize well on totally different data sets. And for that, we are creating data that has different sizes, different data distributions, and also generate queries that should capture lots of different operator varieties. What we also do is that we take data compression and encoding into account. So we, in our database system HiRise, we have the choice between 6 different compression techniques. We can apply really heavyweight or lightweight compression, and we are building cost estimators for executing data that is compressed and evaluated. And last but not least, we want to make that reproducible and release in the end the calibration framework for generating the data, the models that we trained, and all of this integrated into our database system HiRise. So I think we have a little bit of time for some really preliminary results on that. With the first experiment, I wanted to look at if the calibration data we are generating is constructing models in the end that are able to generalize. So what we did is we trained our models on the calibration data we generated, and we also trained the models on the TPCH benchmark, and then we compared the results for predicting query execution times in the TPCH benchmark. This is for the scan operator, and we can see on the x-axis the predicted execution time, on the y-axis the actual execution time, and the red line is a perfect prediction. Our predictions are the blue spots, and TPCH model that is trained on TPCH data is, are the orange spots. We can see that the TPCH model is performing better, which is not surprising because it was trained on TPCH data. But our calibration-based model does not perform much worse. When we look at the metrics, we have the mean absolute percentage error, where we are a bit worse. We have the number of predictions that are not more than 50% of the actual value. And we have another metric, the logarithm of the accuracy value, which gives a hint on whether we are over or underestimating with our model. What we also did is then we took the model that is trained on our calibration data set and on the TPCH benchmark and looked at the results for predicting scans from the TPCC data set. And we can see here that our model performs much better than the one trained on the TPCH data set, which is also not surprising again, But as I said, these are first results for our preliminary results. Running short on time, we are skipping the last part on the evaluation, and I just want to quickly go over the next steps in our work on that. First, we want to improve the calibration data and curves we are generating to speed up the process of generating observations for training the models on even further. I think we can improve the model performance by applying some hyperparameter tuning. We want to evaluate our cost models with real-world enterprise workload we have access to, and in the end we want to investigate if we can incorporate concurrency in our cost estimations and predict concurrently running queries. Thank you for your attention.
I want to ask a really unfair question. So, the cost model is more accurate. Does it lead to better query times? Like if I plug it into an optimizer, do I get better latency?
Yes, we had some first results of that as well, because looking at the different encodings, we could find a better configuration in which all the different predicates are executed based on the actual encoding of the data. But as I said, there are also other use cases apart from query optimization, like having more accurate estimates for several database systems or cost predictions.
So, just a short question. So you said you had many different kinds of configuration, and I guess some were better for your workload and some were worse. So I'm wondering if there's a trade-off. The better configurations are more difficult to estimate based on your models. So, and the more simple or the less efficient configurations are maybe better to estimate. Is there that trade-off?
Configurations? What exactly do you mean by configurations?
Encodings, compression schemes, how you set up your data.
Yeah, so I don't know if I answered the question correctly, but I believe that, for example, heavyweight compressions were totally different than the lightweight ones, dictionary encoding, compared to zip compression, for example. And this is much harder to predict the execution time because there are much more steps involved and there's a blockwise compression, so it's much harder for the model to get that.